Hello, today we are covering lesson 11.4, areas of regular polygons and composite figures. You guys will be able to find the perimeters and areas of regular polygons and find perimeters and areas of composite figures. So our new vocab today is center of a regular polygon, radius of a regular polygon, apothem, central angle of a regular polygon, and composite figure. So part 1, areas of regular polygons. In the figure, a regular pentagon is inscribed in circle P. That means this is all the way inside the circle, and the vertexes are on the circle. You could also say circum P is circumscribed about the pentagon. The center of a regular polygon and the radius of the regular polygon are also the center and the radius of the circumscribed circle. So notice center P is center for both of the pentagon and the circle. The radius is the same for both as well. A segment drawn from the center of a regular polygon perpendicular to a side of the polygon is called an apothem. So segment PF is considered an apothem. Its length is the height of an isosceles triangle that has two radii as legs. So if you look here, we have a triangle we can draw. We know this has to be an isosceles triangle because the legs are radii, and all radii are the same. And the apothem is the height of that triangle. It drops down at a 90-degree angle. It is perpendicular to the base. A central angle of a regular polygon has its vertex at the center of the polygon, and its sides pass through consecutive vertices of the polygon. The measure of each central angle of a regular n-gon is 360 divided by n. Now when I say n-gon, that just means how many sides there are in the polygon. So if there's 50 sides, it's a 50-gon. Things like that, all right? So to find the central angle, first of all, we'll draw one out. It's from vertex to center, center to vertex. Consecutive vertexes, to be exact, and the central angle of the regular polygon is 360 divided by how many sides there are. There are 7 sides in this particular polygon. So if you divide those, the central angle is 51.43 degrees for that angle. Now we're going to use this, so make sure you know how to do it. We can draw the central angle of this regular polygon here. This is just one of them. All of them are actually congruent. That's another central, this is another central, that's another one. They're all congruent. This time it's an 8-sided shape, so we take 360 divided by 8. We end up getting 45 degrees for our measure of our central angle. So now we're going to work with our vocab. In the figure, pentagon PQRST is inscribed in circle X. It means it's inside of the circle. Identify the center, a radius, an apothem, and a central angle of the polygon. Then find the measure of the central angle. So the center, pretty easy to name, is X. A radius, there's 2 of them drawn out. I'll probably write both of them, X, or QX or XQ, either way. And X are our radius that are available for us. They go from center to the side of the circle. The apothem is from the center to the side of the polygon, specifically at a 90 degree. So XN is the apothem. And the central angle measure, it's a pentagon, a 5-sided shape, so we take 360 divided by 5, and we get 72 degrees. All right, in the figure we are going to find the central angle measure of hexagon ABCDEF inscribed in circle G. So what is the angle measure here? We have a hexagon, so we say 360 divided by 6 is actually equal to 60 degrees for our central angle measure. All right, now we're going to use all of those pieces. So there's two ways we can solve these. If we are given the apothem and the base, that is the easiest amount of information to be given. We are in this case. The first way you can solve is actually just finding the area of one triangle. And then because these are all congruent triangles, multiplying it by the number of sides or the number of triangles there are. So it says the top of the table shown is a regular hexagon with a side length of 3 feet and an apothem of 1.7 feet. What is the area of the tabletop to the nearest tenth? So I'm just going to find the area of the triangle. That is base times height divided by 2. So 3 times 1.7 is 5.1 divided by 2 is 2.55 square feet. That is just this triangle though. To find the whole thing, we then multiply by 6. And our whole area is 15.3 square feet. All right. We'll do another one that way. Once again, we are given the apothem and we are given the base. So I'm going to find the area of my triangle. So that's a base times height divided by 2 to find the area of the triangle. So that is 1.5. We once again have a hexagon in this umbrella. So we can multiply the area of the triangle times 6, because there are 6 of them, and you end up getting 9 square feet as your area. Okay, so we actually have an equation. Instead of breaking it into however many triangles there are, you can use the equation to solve. So it says the area of a regular n-gon with side lengths s is 1/2 the product of the apothem and the perimeter. So that is this equation. That's the one I honestly like to use, but this is actually equivalent to that. N times s, or number of sides times the side length, is equal to p, the perimeter. You just break it down. I like this one because I can think about just taking half the apothem times the perimeter, and I know how to find perimeter pretty easy. So let's try some. We're going to find the area of the regular hexagon and round to the nearest tenth. So things that we need the apothem, we need the side length. That'll get us our perimeter. We'll start there. We'll probably figure out, we need our central angle to help us figure some things out. I'm actually going to find that one first. This is a hexagon. There's 6 sides. This also says that. I'm going to take 360 divided by 6. I know my central angle is 60 degrees. Now something I want to point out. Notice, we are not given our apothem. That means we have to find it. We're also not given enough information to just find it using the Pythagorean theorem. Now, because this is a 30, 60, 90 triangle, if you notice, we have 90 here. Half of this 60, because I'm only looking at this triangle right now, is 30. And that leaves this to be 60 degrees. So our central angle, our total central angle is 60 degrees, but then we end up using 30 here. I know that this guy is half of 5 meters, so 2.5 meters. I still need to find our apothem. I'm going to label it A. And just because this is an equilateral triangle, I know these are all the same, which means this is 5. So there's actually a couple ways we can solve this. You can do Pythagorean theorem to solve for A, or you can use special right triangles. I'll quickly show us both. So here's our special right. I'm going to set up a proportion to solve. And you can go ahead and make this a decimal if you choose. We end up getting 4.33 is our apothem. So now we actually have enough information to solve for our our area. So our apothem is 4.33 meters. Our side length they started by giving us is 5. Our perimeter we just add up, so 5 plus 5 plus 5 plus 5 plus 5 plus 5. Or you can take 5 times 6. 5 times the number of sides is 30. We are going to want to use our equation. Area equals half apothem times perimeter which equals 64, and it wants nearest tenth, 0.95, but these round up and that rounds up, so 65.0 square meters is our area of our hexagon. Now I did say because it was an equilateral, we did have enough information to solve using Pythagorean theorem, so real quick, I'll show you. We have apothem squared plus b squared is 22.5 squared equals 5 squared. So 2.5 squared is equal to 6.25. So we end up getting a squared is equal to 18.75. And the square root of that is the same thing as the square root of, is the same thing as the apothem we found using perfect right triangles. All right, so we have another one, but are given different information. We are going to find the area of the regular pentagon this time and round our answer to the nearest tenth. So I want to start out once again finding the central angle. I'm going to take 360 divided by 5. 360 divided by 5, let's see if I have it, is 72 degrees. So we have 72 degrees here. Now, I want to separate this out into just a right triangle for a minute before I move forward. So in my right triangle, it is actually half of that 72 degrees, or 36 degrees. I have 9 centimeters here. I need to find both my apothem and my whole base. Now right now I'm only going to find this part of it. But those are things that I need to get. So, unfortunately this time it's not a special right triangle. It is not enough information to do Pythagorean theorem, so I'm going to have to use some trigonometry. So if 36 degrees is my perspective, I am going to go ahead and use sine to find my base. So I have sine of my perspective, 36, is equal to opposite b over opposite B over hypotenuse 9, I should say. I like to think of these as a sort of cross multiplication problem, where it is a proportion, and then I solve it. Now, when I plug in 9 sine of 36, I end up getting 5.3 for my base. I can set up a similar problem, but using cosine this time, to solve for my apothem. Now the A that I'm using here is not for adjacent necessarily, it's for apothem, so don't get that confused. I will cross multiply to solve. It really is a very similar problem. So I have 9 times cosine of 36 equals my apothem, which is 7.3 centimeters. Okay, so I have my apothem. 7.3. I have half of my base, this guy, B, D. I want the whole thing AB, so I'm going to double it and get 10.6 centimeters. And now I have enough information to go ahead and solve. My area is equal to half times my apothem times the perimeter. Now 10.6 times 5, because it is a pentagon, is equal to 53. And then I just solve. So half times 7.3 times 53 is equal to 193.45 square centimeters. If we look back a step and hadn't found our apothem yet, you could have actually solved for the apothem using Pythagorean theorem if you would like to. You don't have to use trig for both. If you have enough information to use Pythagorean, you can use it. All right, one more like this. We are going to find the area of the regular octagon, round our answers to the nearest tenth. So you're given the center point. I'm going to go ahead and draw in a triangle and then also split that in half, my central angle, I should say. That way I can visualize what's going on. So it's an octagon. I'm going to take 360 divided by 8. That gives us 45 degrees for our central angle, which means when I redraw just my right triangle, let's try that again. There we go. My angle of my right triangle is half of that, or 22.5. And just this portion is half of the whole side of my octagon, so 1.5 here. And I want to only find my apothem. Notice I have opposite and adjacent from my perspective here. So I'm going to use tangent of 22.5 is equal to opposite over adjacent. I will cross multiply to solve. So I need to take 1.5 divided by tangent of 22.5, and my apothem equals 3.6 feet. Okay, so this one, the apothem was actually all I had to find. I already have the side length. I do need to find the perimeter, I should say. But that's not too hard. I take my apothem times my perimeter. The side length is 3. There's 8 of them, so 24. I take half times 3.6 times 24, and I get that my area is equal to 43.2 square feet. Yep, square feet. All right. So that is how you find the area of regular n-gons. We are going to switch over to something a little different, although I will say probably easier. We're going to find the dimensions of irregularly shaped pool. So, what is the area of the surface of the pool? It's pretty simple when they go ahead and split it up for you like this. You can visualize there's 4 different shapes making up this. 2 semicircles, a rectangle, and a triangle. We know how to find the area of each of these shapes, so let's do it. So I'm going to say rectangle, area. To help me remember, I'm going to say area is equal to base times height. So I take 32 times 16. Now, 32 times 16 is equal to 512. So 512 square feet is my rectangle. Then I need to take my triangle area. That is base times height divided by 2. My base, I'm going to say, is 32. My height is 15. Divide that by 2. Oops. I end up getting 240 square feet. And then my semicircles, there's 2 of them. Need to find the area for those. The area for a circle is pi r squared. So I take pi times my radius, so I only want half of this, so half of 16 is 8. Squared, I'm going to do 64 pi. I take my 8 squared first. And I get 201.06 square feet. Now notice that is the area of 2, or a whole circle, but because there are 2 of them, if you put them together you get a whole circle, so you can just leave it like that. And then add all of these together, and you get your area for the whole irregular shape. All right? We can do a similar problem. This time we're going to round the area of the figure in square feet, or find it, and then round to the nearest tenth if necessary. So there's 2 ways you can do this. I'm actually going to not split it into 2 triangles, a rectangle, and a semicircle, but I'm going to split it into a trapezoid and a semicircle. So, trapezoid area is equal to half times height times base 1 plus base 2. So I'm going to fill in my info. Half, my height is 8. Base 1 is 18. Base 2 is 28 for this whole thing. Go ahead and solve. I'm going to reduce this down to 4. So 4 times 18 plus 28 is, oops, not that. 46, I believe, but I will check. Yep, and then I will multiply that by 4, and I get 184 square feet for that area. Not total area though, almost forgot. I still have to find the area of my circle. So I found the area of my trapezoid. Sometimes it's easier to color what you finished. I need to find the area of my semicircle. So this is pi r squared, but because it's a semicircle, I need to divide by 2. My radius is 9. So I have 81 pi divided by 2. So I get that this is 127.23. And then, oops, I can add 184 to that, and I get 311.23 square feet for my total area. Alrighty. This next one, we are going to find the area of a shaded figure. There's a couple ways you could go about this. You could split it into different shapes if you wanted to, and find the area of each of those and add them. You could split it a different way, but similarly. Or you could find the area of the whole entire thing and subtract out the non-shaded area. There is something that's a little tricky on here. They don't tell us what the distance is here. We do need to have a distance there, so I'm just going to assume that is also 25 feet. I wish they had told us, they didn't, so we'll just assume it's 25 feet. So we can find the length of this whole side. It's 25 plus 100 plus 25, so that's 150 feet. And we need to find the length of this whole side. It's 25 plus 20 plus 25, or 70 feet. So to find the area of the whole thing, we take 150 times 70. And we get 10,500 square feet. We can subtract out the other one, so we have 100 times 20, or 2,000 square feet. Subtract them, and you have your answer of the shaded region, 8,500 square feet, as your area. And lastly, in interior design, Kara wants to wallpaper one wall of her family room. She has this fireplace in the center of the wall. Find the area of the wall around the fireplace. So we need to find the area of the gray shaded region. Same thing goes here. We can find the area of the whole thing. And then we can find the area of the fireplace. And then you can subtract. Get 156 square feet for the area that she will wallpaper. All right, that's all I've got. Have a great day.